go through the basic theoretical stuff of instrumentation. And there are two ways to produce voltage. Voltage source can be produced from electrodes of different materials. So electrodes are conductors which produce current. And another way is electrolytes and battery for produce DC current. Another way is through the relative motion of conductors, we generate called generators and produce AC current. In series, the voltage drop across each resistor is a ratio of voltage drop, and so basically in series, the voltage is decreasing at each stage when there is a resistance. Rheostat is a piece of conductive wire used in order to create a variable resistance, and its resistance changing with the length of the wire used. When a rheostat is used as a potential divider, it's called potentiometer and can be drawn as so. On the right hand side, you can see an example of resistance in parallel, and the distance between them is given, and the total resistance is given by the sum of the parallel plus the series one. The sum of these two separated will be the total two resistance parallel. And general sinusoidal waveform as a function of time is written. So sinusoidal form can be written as a function of time, and it's like this. This is the formula where a is the amplitude, omega is the frequency, and phi is the phasor. A certain element may have voltage and current. If one is sinusoidal function, then the other must also be sinusoidal, but due to the different, but with the different, of course, with different phase and magnitude. If the current has a higher phase than voltage, then is said the lead to the voltage. It means lead to the voltage means that the current has a higher phase than voltage. Voltage and current in any different, the sum of the sum of the voltage current is given by Kirchhoff's second law and first law, which we already know. When the voltage are added in corresponding direction and potential difference across the same direction, opposite to the direction, here the current in the same direction, V, and therefore the potential difference across resistors will be in the opposite direction. So we already did this in the previous, so we must skip this. So AC circuit analysis. So this is the formula of AC circuit. Voltage is equal to resistance over time derivative of current plus 1 over C I. AC circuits have voltage of reversing, so AC circuits have voltage of reversing polarity because it's alternating, and we have positive to negative and negative to positive. Therefore, the voltage and current are function of time. General solutions are therefore written in a sinusoidal form, but they are difficult to work in time domain, especially with complex circuits and multiple frequency. As a result, we use the complex number. A circuit therefore there are more than just resistance, real number of impeding flow of current, which is the real number of impeding flow of current. There is there is that of inductors. In fact, there is inductors, conductors self-induced. So inductors are basically self-induced conductors self-induced by magnetic field of current, and capacitance, electrostatic charge induced by voltage between two conductors. And these two form the imaginary part of impedance. So inductors and capacitor form the two imaginary part of the impedance, and therefore AC circuits are simplified using impedance to represent resistance to flow. So AC circuits are therefore simplified using impedance to represent resistance to flow, and working in frequency domain instead of the more complicated time domain, which still can be used, but you have to use the Fourier analysis for the time domain. But if you use frequency domain, it's much more simpler. And this is an example of voltage where it's A sine WT plus phi, and what you get is what you get outside. So what I'm saying. Amplitude is not the best representative of fluctuating current voltage. Amplitude is not the best representation of fluctuating current voltage. Therefore, use RMS, root mean square values. So this is the formula. That's all you have to know. Let's post this for the first page. Now we'll move to the second page of the revision. So capacitor. Capacitor stores electrical charge. So capacitors store electrical charge. The simplest one are made of two metal strips with insulator. So the insulator is a dielectric material which is insulating, which is in between the two metal, and it brings two conductors close but separated by insulator, therefore holding electrical charge. So it holds capacitor electrical charge. Capacitor is therefore the ability, so to hold this charge, and it's measured in farads. charges at electrons stored on a plate. So charging is occurring at electrons stored on a plate. Voltage builds up. So voltage builds up and is proportional. Voltage builds and is proportional to the charge Q. And the constant of proportionality is the capacitance, is the ability to hold charge. And this is the formula for capacitance, and it's proportional to the area. So higher is the bigger is the area of the place, the more charge it can accumulate, and the it's inversely proportional to the distance between the plates. So small distance means high capacitance, and large distance means small capacitance. And this letter here is permittivity of free space, and is 8.85 10 to the minus 12. And we need to know that time constant is due to charge building up, therefore a function of time and Vt, because time constant, so charge and are built up over time. And this is the formulas that you need to remember and apply. Inductance is the ability is the ability of a conductor to store magnetic energy. It's the ability of a conductor. So it's the ability of a conductor to store magnetic energy. To increase inductance, we increase the number of coils and we increase the area, so we can store more energy. But to decrease it, you just so to increase, you also decrease the length. So less length. So the shorter it is, the more inductance it can conserve. Where, and this is the formula that you remember. L is the self-inductance and is measured in henries. U is the mu is the permeability, and N is the number of coils. So current traveling through a coil induces an EMF which travel against the current, so it's opposite direction. Induced EMF, the induced EMF is proportional to the rate of change of current, and the constant of proportionality is the self-inductance. So induced EMF is proportional to rate of change current. The average EMF induced in each turn is the number of turns over time. The average EMF of the whole coil is the number of turns over time times the number of coils. So it's pretty straightforward. One is turns over time and one is turns over time, but times number of coils. And this is the formula you need to remember for this. So that's it. Now we'll move to page 3. Page 3 is about further circuit analysis and phasors and impedance. So as I said before, RMS is an effective method to get the value of voltage and current in alternating circuits because their values are continuously fluctuating. And voltmeters, ammeters, and watt sockets are used to display the RMS values. And similarly, since we have an average value of voltage and current, we can get also an average value of power using the following formula, which is P average is equal to V RMS and I RMS. And the wavelength changes into RMS. And change pulse width to modulate delivered power instead. So we use the change pulse width to modulate the delivered power. So we change the pulse width rather than the modulating the amplitude, which is less effective. Therefore, we use the change pulse width to modulate and therefore deliver the power. And changing changing the pulse width keeps the frequency constant, and as a result, we get an effective value of RMS. And the value is RMS is equivalent to the steady DC value, which is the direct current. Therefore, the same electrical power. And and as a result, if we have something displaying 10 voltage in DC power, it means it's 10 voltage in AC supply. It means the light above the light will bulb the same brightness. Now we'll talk about phasor. Phasor is a vector quantity and it's a mathematical representation of a phase of the alternating current. So basically what it does, it converts it converts into phasor and converts into phasor or spatial domain. So what it does, it reduces the sinusoidal function into two parameters, so the amplitude and the phase. And so yes, it's written in terms of amplitude and phase and the angular velocity, and it has both magnitude and direction. So for example, if you take two sine waves, you use the difference in the angle x-axis to create a phasor arrow with magnitude and direction. That doesn't really make sense, but what it does is that from this graph we can draw like the angular rotation and calculate the difference. These are the two formulas you need to know. And of course, there is an example here graph the current is lagging by an angle of 30 degrees. So it's saying that current is behind by 30 degrees, but it doesn't look like from the graph. It looks like that current is ahead, but in actual reality, voltage is ahead. And we say voltage is leading by this angle because voltage actually is ahead, not the current, because it's based on the amplitude and not from the horizontal length. Now, depending on which one you take as a reference, we create one of the following phasor diagram. So, if you take voltage as a reference point, then the current is we have to go down for the current because voltage is ahead, so we go down by 30 degree. Similarly, if we take current as a reference point, we know that voltage is ahead, which is leading by this angle. We see the 30 degree, and this is the diagram that show that this nonsense here. Now we're moving to the next page, page 4. So at zero time, we can see the red diagram is at zero, and the red one represent the, I guess, the sign. Yeah, the sign, of course. And the blue one at zero is extended by an angle of 45 degree. So V at the beginning is A sine WT, and V voltage is later is A sine WT plus pi over 4. So pi over 4 is the phasor, is the amount by which it shift respect to the initial voltage. Now, current has a higher phase than voltage. It means the lagging sine omega plus pi over 4 is sine W lagging. Lagging means higher. Okay, so to find a phasor, we just use this formula here, and it's quite straightforward. Now let's move on to impedance. Impedance is the magnitude of complex impedance. So this impedance is represented by the following expressions, and now I'm gonna explain this. So phase is shift by which the current is ahead of voltage. So phase is shift by which the current is ahead of voltage. So in this equation, R is given by zeta cos theta, and it's a real part, and it represents the resistance. X is given by z sine theta, and it's the imaginary part, and it's defined as the reactance. And then we have Z, the overall impedance is given by the square root of R squared plus X squared, and it's the ratio of voltage amplitude to current amplitude. So it's the ratio between the amplitude of the voltage and of the current. And if it's for a sinusoidal function, the magnitude is provided by the ratio of the voltage and of the amplitude, as I said before. And theta is the argument, and it's a phase difference between the voltage and current. You need to know also this complex part, so you need to remember this. For the capacitance, Z is the capacitor, and the L is the inductance. Those are the core components of the impedance, and they can be written in this. So as I was saying before, this is the formula you need to know. And for a look at this graph, from the capacitor graph and the inductor graph, it's possible to see that for the capacitor graph, the current is leading. The current is represented by the blue wave, and is leading because it's ahead. And the bottom one is inductor, and the current is lagging because it's apparently behind respect to the other source. And if you represent this in the impedance form, signs are reversed. So this is how you would be probably write this: JC for the conductor and JL for the inductor. The magnitude of the current is found using the diagram, and in the y direction is the difference between IL and IC, of course, and the x direction is being IR, and therefore the angle and magnitude can be found using trigonometry, which is quite pretty straightforward. And to solve this kind of question, I use the rule V equals IZ, and instead of resistance, we have the impedance now. And in parallel, some of the branch uses the same rule, and some of the branch individually. And for to find the total impedance, use the multiply by the total current, and that's how you find the voltage in each branch, and so on. Now let's move to page number 5, and we're going to talk about Fourier analysis. So we know the general function signals can be represented or approximated as a sum of more simple function, and this process is reversible. So it's a method to decompose complex function in simple sinusoidal function, and vice versa. So any wave can be written as a sum of sine function and with varying phase and amplitude, And this decomposition is called Fourier analysis or transform. So transform of Fourier analysis means a complex function is decomposed to simpler function. Rebuilding the more complex function, on the other way, the sum of like small function to build a complex function is called the Fourier synthesis. Synthesis or synthesis, I'm not sure how to pronounce this. And when the input domain in time is and when the input is in the time domain and output is in the frequency domain, the transform of the signal is converted using the following formula. So to convert from time to frequency domain, use this formula. Vice versa, if you want to convert time into frequency, use this formula. Fair enough. Therefore, the Fourier transform takes the continuous function of time and convert in the frequency spectrum. And when the waveform is not in the sinusoidal form, then you have to take three steps to convert this into sinusoidal form. So step number one, the Fourier decomposition of the signal, and then step number two, calculate the circle's response to each of the sinusoidal. So you have to calculate the response on each of the sinusoidal components. So you need to find the response on each of the sinusoidal components, and the third one is the superposition theorem to find the missing part. So response in any branch of linear circuit having more than one independent source is equal to the sum of the response caused by each independent. No, I didn't get this, but we'll go through later on. And in this graph, it's possible to see a large wave decomposed, a big large one decomposed in a smaller one. And this is an example for called this fundamental and three odd harmonics. So it has been decomposed using the Fourier analysis. Now the frequency response, similar to the transfer function, which is defined as the way a system input is related to the output, the frequency response is the response at different frequency for the domains and whether the signal at this frequency are amplified or attenuated or stopped. So basically, we can find out if the signal at a specific frequency is amplified or attenuated, which means reduced. Passive circuits, where there are no active components such as the amplifier, the frequency response for passive circuit, the frequency response range between 0 to 1. And this is a diagram showing the input, output, the H, so phasor input, phasor output, and the frequency response is this one, and that's the correlation, this equation. If the response is 0, means the signal is stopped, input doesn't reach output. If the response is 1, means the signal is amplified and input is reaches output. And anything between 0 and 1 means that it's reached with attenuation. Now we're moving to page 8, passive filter circuits. Passive filter circuits are basically circuits constructed from resistor, capacitor, and inductors to gain certain range of frequency and frequency transform input signal according to the certain range of frequency transform input signal according to the frequency response. And as the input goes into the frequency response, it gives an output. If the amplitude is 1, input reaches output. If the amplitude is 0, input doesn't reach the output. If it's in between, then it's reached with reduction of strength of signal. Through the use of inductors, capacitor, and resistor, passive filter alter the input of a system. The input of alter or change the input of a system in order to filter or gain a range of frequency. Transform depends on the frequency response and as a result on the transfer function. The use of capacitor inductors will cause the phase. So the use of capacitor and inductors will cause phase changes. So it means voltage and current is lagging by pi over 2 and affecting the input and output relationship of any filter. So we can have four type of cases. So low pass, high pass, band stop notch, and band pass. So low pass is allowed to low frequency whilst so it allows the low frequency whilst attenuating, which means stopping the high frequency. And the filtering noise is from the transducer, sensors, or actuator. And the Fourier analysis is to analyze the frequency spectrum and the noise and helps to find out the noise from essential components of signal. And basically it filters noise and it keeps the important signals. In the high pass, it allows high frequency while attenuating, which means stopping the low frequency. So an example of this is a DSL modems have high-speed data communication. Then we have the band stop or notch. So allow high and low frequency, but attenuating frequency within a certain range. So it stop frequency at a certain range. So then we have the band pass. So allow again it's allow this time only a single band of frequency to pass, and stop frequency above and below that band. So only a single band is allowed, and anything above or below is attenuated, which means stopped. And this is the basic terminology that you need to know. So filter order means the number of stages the filter defines the number of stage of the filter. So and it defines the complexity of a filter. The bandpass frequency range for which allow information to pass from 0 to 1000 amplitude not less than 3 BD. Stop band filter signal range. So pass band frequency range which allow information to pass. So pass band, so it allows information to pass. It's between 0 to 1000 hertz and amplitude is not less than 3 decibels. Stop band is a filter signal range which is attenuated. Stop band, so it's filter signal range which is attenuated. Then we have transition band, so area of filter between pass and stop bands. So it's area of filter between pass and stop bands. Then we have cutoff frequency, the filter at which filter breaks. Any changes between pass and transition, vice versa. So this is a graph of frequency. This is an example of setup for the low pass filter. So current is same as it doesn't pass filter, so cancel in V out in V in. So current is same as doesn't pass filter, so V out is equal to V in. Therefore resistance and capacitor are in series, and V is same as voltage across capacitor parallel. So frequency response is 0 to 1, and the frequency at 0 we have H is 1, and from the frequency infinity the H is 0.